Hello everyone. In this video, we're going to start talking about lesson 4, which is probability and probability distributions. And so this lesson is really a key lesson in bridging us from the beginning of the course, which was really the first 3 lessons, to the rest of the course, which will be really lesson 6 and on. We'll use the information that we learn in this chapter in many different ways. So this is really a key chapter that you pay close attention to. So we're going to talk about very quickly probability in general. So I've mentioned the word probability a bunch of times before in conjunction with proportions and percents. And that was on purpose because a probability is sort of like in this class we can basically think of it as a proportion or a percent, but it has a lot of different meanings in different situations, and it is a very important idea in statistics and really in general. We all know about probability in one way or another, and so we're going to talk about it formally for just a second here. Okay, we use probability in statistics to try to understand how random events work. And so the terminology that we usually use is that we use probability to quantify randomness. Okay, so if I were to play a game that involved flipping a coin, I don't know the outcome of the coin flip. And so I don't know what's going to happen. But I can try to understand how likely the outcomes are, whether I win or lose or whatever, with some certainty using probability. Okay, so for instance, if it was a coin where I flipped, if it was a game where I flipped a coin once, if it's head I won and if it's tails I lost, I would say that I have a 50% chance of winning and a 50% chance of losing. Then I'd use that information to decide whether I want to play the game or not. Okay, and so in there I'm quantifying the uncertainty about the game with probability. Okay, all right, so end of rant of why probability is important in statistics. I could talk for hours about how important it is, but it's not useful for us if I do that. Okay, so there you go, quantifying randomness. So when we observe a small number of random phenomena is what I call it. Here you can think of it, if I observe a small number of coin flips or rolls of a dice or really anything where the outcome is random, meaning we don't know the outcome before it happens, okay, the behavior may look quite different than what we expect. Okay, so for instance, if I flipped 4 coins, or if I flipped a coin 4 times, and all of them landed on heads, is that surprising or not? Okay, so think about that for a second, and if you need to do it yourself, find a coin somewhere, if you have a coin at home, and flip it a bunch of times. See how many times 4 heads comes up, or maybe 4 tails, or whatever comes up. It turns out that it's not so surprising to see 4 of the same thing happen, even with a fair coin. So you may think, well, if I see 4 heads in a row, that coin that I flipped may no longer be fair. And that's a fairly reasonable assumption, but it turns out it might not, it doesn't necessarily mean that the coin is unfair, and we can use probability to say how likely that happens. And so I know that might not be a great example, but we'll use it in different language throughout. what we're going to do, or the basic idea of statistics that I'll talk about more in lesson 6, is that I've got this random phenomena. I've got this thing that I want to understand, and I'm going to understand it with probability. Okay, and then this sort of for lack of a better word, situation that I want to make some statement about, or I want to find out some information, and I know how it operates under said normal operating conditions. Okay, and that maybe I know how a fair coin is supposed to operate. Okay, and when I mean that, I mean I know, using probability, how things are supposed to react. So a nice example, or a quick example, would be if a coin is fair, I would expect, or we say that it's a 50% chance that it's heads, or 50% chance that it's tails every single coin flip. Okay, and if I flip a coin 1,000 times, then I have some idea. If the coin is fair, I've got some idea about how that coin should behave. Okay, if we talk a lot about probability, and you should know this to some extent in your head, that if I flip a coin 1,000 times, it is very unlikely, or rather, I would expect that around 500 are going to be heads. But I know that when I flip the coin 1,000 times, it's probably unlikely that I actually see 500. I may see 480. I may see 520. I may see even maybe 600. Even when the coin is fair, there's some randomness involved. But, for instance, if I flipped a coin 1,000 times and I saw 900 heads, does that give me enough? Is that enough? Is that far away enough from what should happen when a coin is fair to warrant me to make the statement that the coin is not fair? Okay, so again, that may be a little over your head at this moment. We'll come back to that later on. Anyway, the point that I'm making in this slide is that when I have a small number of events, I flip the coin a small number of times, I can see behavior that looks very different. Hence, 4 heads in a fair coin happens all the time. But as I take more observations, the behaviors should tend to what you expect. Meaning, if I flipped the coin 100,000 times, the number of heads should be fairly close to 550,000. Okay, if I flip it 100,000 times, the heads should be close to 50,000. If it was somewhere like 20,000 or 80,000, then that would give me pause. So probability, or the definition that's sort of where we're going to work with, is the long-run proportion of the random phenomena. For a coin, if I flip that coin an infinite number of times, then the number of heads I should see are about half of however many times I flipped it. Okay, for some humongously large number. If you don't really understand what I said, that's okay. You'll be able to make it through. So how do we use probability in this course? So what we're going to do, in the same vein as what I've been talking about before, is we're going to use a probability model. And I use this word model again. I used it in lesson 3 to mean something similar. We're going to use a probability model to approximate reality. okay, to approximate reality. So what I mean by there is I can come up with a mathematical equation that describes the probability of different events happening for a coin flip, or for a dice roll, or for anything random. Okay, I can use an equation where I plug in some numbers and then it gives me a probability out of something happening. So a probability model specifies the possible outcomes for a what I'm going to call here is a sample space. We don't need to worry about what a sample space means, and provides assumptions on which the probability calculations for events composed of those outcomes are based. Okay, that was a long definition, and you don't need to worry about that. An example will do just nicely for this. So if I have some x, okay, so we're going to see a lot of capital letters of x, y, and z, and I'm going to call them, when I talk about them, I'm going to call them random variables. Okay, so they are variables which I'm interested in, and I don't know the outcome of them, so I'm going to call them random variables. So suppose this random variable x represents the result of a six-sided dice roll. Okay, the probability model would give me all possible outcomes of that dice roll, 1, 2, 3, 4, 5, and 6, and the probabilities that each of those things happened. Okay, and so something that you'll see down here that I want to take note of is that I have this p, and then I have parentheses, big X equals little x. This is not a function like you'd see in a math course. Okay, or it is in reality, but we don't need to think of it that way. Okay, so this is not a function like we'd see in a math course. This p stands for the probability. So I'd read this as the probability that I see an outcome equaling one of the possible ones up here. So the probability that I see a 1, the probability that x equals 1 is 1/6. Okay, 2 is 1/6, so on and so forth. So the reading assignment is here. This is an optional reading assignment. There's a lot of probability that goes into what we do, but we're going to skip over most of it. If you are really interested in it, okay, you can read pages 200 through 236, and they'll give you a really nice introduction to probability. Okay, so what we're going to focus on now for just a little bit longer is how probability models approximate reality. So for instance, here is some data on heights of men and women. So you'll see heights of men in the blue, okay, heights of women in the pink, and I have histograms, and then you'll see also some smooth curves in the back. And so what we're really interested in are those smooth curves in the back. But I have histograms of each of these men and women. And so the process of this probability model, although not 100% true, is that we are essentially smoothing out a histogram to get a smooth curve. So the question that I would ask myself is, what kind of functions or what kind of equations can I use to approximate those histograms? So the histogram is reality, and I'm trying to use an equation to approximate what that reality looks like. And so I can do that, and here are those curves. Okay, and so those curves approximate the reality of what happens, and I can use those curves to find probabilities, which is what we're interested in. Okay, and so if you want to look at some practical significance of this plot, you'll see that, of course, women are generally shorter, than men. And also, what you'll see is that the heights of men are more spread out than the heights of women. Okay, that's not totally relevant to our uh, discussion here, but nonetheless interesting, and something that you should always be doing in this course is when we see a plot, when we see a graph, think about what it means practically to you. Okay. So in statistics in general, we won't see a lot of this in our class because it's just an intro one. But in statistics, there are a bunch of different equations that model a bunch of different real life situations. And so here are a non exhaustive but lengthy list of different probability distributions, which are what those models are called, that approximate different realities. Okay, so this is where I'll stop. And next time, we'll start talking about the special probability model that we'll focus on, which is called the normal distribution.